So now we are ready to prove the factor theorem. So what does the factor theorem say? So factor theorem say that if f from G to H is a homomorphism of groups, right? And N is normal in G and is contained in the kernel of F, then this mapping F bar from G mod N to H defined by AN is mapped to the image of A under F. This is a unique homomorphism. So first you have to show that it's unique. There's only one such mapping. Next you have to show that it's a homomorphism, which is actually quite easy because it follows from the homomorphism, from F being a homomorphism. There are also two other statements they have to add. The image of F equals the image of F bar. The kernel of F bar is the kernel of F mod N. And finally, that F bar is an isomorphism if and only if F is epi and N is the whole of the kernel of F is N, right? So there's so many statements that we have to prove. So let's start with F bar being, so let's start here. Start with being uniqueness and being homomorphism. So let's start. Start with F is well defined. So we showed that if AN plus BN implies that AF bar, okay. Okay, let's start with F bar is well defined. So if we have two elements A and B with who belong to the same coset, we have to show that they have the same image under, what do you call that? Under F bar. So what does it mean? So suppose AN is equal to VN. So these are elements of, these are cosets, elements of G mod N, diba? Suppose that is true, then what does it mean? By definition, it means that A inverse P is in N, right? And if you multiply both the left side by A, it means that P is in AN, right? If P is in AN, then P equals AN for some n in n. But n is contained in the kernel of f, right? N is contained in the kernel of f. What does that mean that n is contained in the kernel of f? That means that n, the image of n under f is mapped to, or equal rather, equal to the identity in H. That's what it means, right? Okay, so B is equal to AN. So let's apply, what do we apply? F bar. Is it F bar? Or rather F. Let's apply F first. So, F. Why do we have dots here? 1 dot, 2 dot, 3 dot. So F, let's apply F. Then F of B equals F of A N. But since F is an isomer, rather than a homomorphism, then it's equal to F of A of N. But again, F of N is the identity, so just F of A, right? How did we define F bar? So F bar of A N equals the image of A under F. So meaning, let's write everything down. Meaning that F of A is equal to F bar of A N. Same here, F bar of B N. So actually, what I should have written here is not, what do you call this? Should not be, should have not, should be F bar of AN, F bar of EN, because the domain of F bar is from G mod N to H. Okay. Okay, so assume that A and B belong to the same coset. We have shown that they have the same image under F bar. So well defined. Well defined. Therefore, F bar is well defined. Okay, so that's for well definedness. Let's proceed to uniqueness. So how do you do that? Suppose there is another. Suppose there is another mapping. Say F tilde from G mod N to H. Defined similarly, so F tilde of A N is equal to F of A, the image of A under F. So if there is such a mapping, you have to show that they F bar is equal to F tilde. What do you mean by what do you mean when two um functions are equal? So we have to have the same, first of all, they have to have the same domain, just it's obvious by definition, and they have to have the same image under for all x in. But what is x here? An, right? For all an in G. Oh, what is this? In G mod n. So show that. Okay. So let's start with f bar of n. So f bar. So let an be in G mod n. Then f bar of an is equal to what is an? This is equal to pi of a, right? But what is but this is the composition. So f bar pi a, which is equal to f of a, right? But f of a, let's go back. Let's see. Is f of a, see here, is equal to tilde f tilde of an. So f tilde of an. Therefore, so they have the same image, right? Therefore, f bar equals f tilde on G mod n, and they are the same function, and therefore f bar is unique. Right? So let me read my notes, right? Okay, we are done with uniqueness. Let's go to homomorphism. F bar is homomorphism. So let's G mod n. So an and gn, not gn, bn. Right. So f bar of an bn, right? But this is equal to abn by the operation on G mod n, right? And then let me think for a while. This is mapped to f of AAB, right? By definition of f bar. And then since f is a homomorphism, it's equal to f of a, f of b. But f of a is equal to f bar of an, and f of b is equal to f bar of bn. Right. And yeah, we have shown that f bar is a homomorphism, which is actually a direct consequence of, therefore f bar is done. Okay, So we are therefore F bar is a homomorphism, and you have shown that F bar is a unique homomorphism. So we have shown that F bar is well defined, it is unique, and it is a homomorphism. Next, you have to show that the image, the fourth one. The image of F bar is the image of F. So what is image of F bar by definition? It is the image of F bar shown. So this is set of all elements P and H such that P equals F bar of AN for some AN in G mod N. Oh, right? That's the definition of the image of F bar. So by definition F bar AN, this is P and H dot P equals F of A, right? For some AN. Of course, if AN is in GN, then it implies that A is in G, right? So you can write P and H such that P equals F of A what? For some A and G. And this is definitely basically the definition of the image of F. Right. So next, how about the kernels? Kernels. This is number 4 or 5? 5. Okay. Rather. 5. So show kernel of F bar mod N. Okay. Kernel of F bar definition sets of all AN and GN such that the image of AN equals the identity in H. Right? What is the image of AN under F bar? Is F of A. Right? F of A equals, right? This is by definition. F of A equals the identity. If F of A equals the identity, then that means that A is in the kernel of F by definition. Right? So A and G mod N. So AN in G mod N such that A is in the kernel of F. That is basically the definition of this, right? If all of the elements in A are in the kernel of F, then this is the notation that we use for that. So therefore, that is true. Now, let's go to the sixth statement. The sixth statement, not consistent, that F is epi for if and only if F is epi. Okay, let's do it slowly, step by step. So suppose F bar is an epimorphism. What does that mean? That means that F bar of G mod N equals the whole of H, right? So suppose this is true, show that it is true. Let P be in H. We have to show that there's an element A in G, diba? Because F, diba? F is from G to H. So pick an element B in H. You have to show that there's an element A in G such that F of A equals B. Okay. Let B be in H. Then there exists an G mod n such that f bar of an equals p. F bar of an equals p. What does it mean? By definition, this is f of a equals p, right? And therefore, f is epi. Therefore, f is epi. On the other hand, suppose f is epi. So this is that direction. Okay. So let P be in H. They have the same codomain. So there exists A in G such that f of A equals P. But f of A is f bar of an. And therefore there exists an in G mod n. Obviously this is an element of G mod n, right? And therefore f bar is P. So we have proven the statement that f bar is an epimorphism if and only if f is an epimorphism. Okay, final statement. So seventh, I think. F bar is a monomorphism if and only if um, f is epi and n equals the kernel of f. Okay. There's a result about monomorphisms that we can use. So the result states that say you have uh, f say f is a homomorphism of groups. F is mono if and only if the kernel of f equals what is that? The kernel of f contains only the identity of G. Trivial subgroup. The trivial subgroup. Okay. So we'll use that result. So let's start with supposing that f bar is 1. Then the kernel of f bar equals the identity in H, right? No. I'm sorry. The identity in G mod n. What is the identity of G mod n? It's n, right? This is the identity element of G mod n. En equals n, right? So that is true. We have to show that n is equal to the kernel of f. Let's try. A is it a kernel of F implies, if I don't live, um, an is in kernel of F mod n. This is by definition. And then what? So an. Why is an in the kernel of F bar? Ah, okay. But, nakakalimot ko, my God. But this is equal to, we've already shown that this is equal to the kernel of F bar. So therefore, an is in the kernel of F bar. F bar. There's a bar here. There's a bar. But kernel of F bar is contains only the identity coset. So we have no choice but to say that an is equal to n, right? And what does it mean that when an is equal to n? It means that a is an element of n. Why is this? Why is this? Okay, so let's try to expound. So what does it mean when an equals n? It implies that an plus en, or en equals an. So by definition, it means a inverse a is in n. But what is e inverse? E. So a plus n, basically. So that's it. If an equals n, then a must be an element of n. So they are equivalent. So that means that you have just shown that the kernel of f is equal to n. Kernel of f equals n. Therefore, okay, let's do the opposite direction. So suppose I'm not really done yet, am I? We also have to show that f ano yun? Actually, yun na. Sakto na day. Sakto na. Sakto. What is the statement? The statement is f is... Actually, I forgot. We have to delete this part. This is not necessary. It's not necessary, actually. F is mono if and only if kernel of f equals n. This should be the one. I'm so sorry. Okay, so let's do that. Let's do the opposite direction. The opposite direction. Suppose kernel of f equals n. You have to show that f bar is mono. So it's enough to show that, yeah. So if we have to show that f bar is mono, diba? you have to show that f bar is mono. It's the same as showing that the kernel of f bar is just the identity, the trivial subgroup. So kernel of f equals n. What is kernel of f bar? Set of all cosets which are mapped to the identity. So f bar of an, the identity in H, right? Because G mod into H. But by definition, this is f of A, right? By definition, um, let me think. Let me think for a while. Feeling na ako nag-over ko. Ano ko? Okay. Ano lagi ko? Samok. Woo! Okay? So suppose kernel of f equals n, then by previous result, kernel of f bar is kernel of f mod n. But since kernel of f is equal to n, then it will just be equal to n mod n, which is just trivial. It's just a trivial subgroup. So trivial subgroup. So what happens is just becomes n mod n, which just contains only one element. N. Just n. Okay, and therefore, if that is the case, then f bar is mono. It's the other way. Just the trivial. There's just one element. This contains only one element, basically, just n. So let's recap. Let's recap. Let's recap. F bar from G mod n. So what have we shown so far? This is a unique homomorphism defined by an f bar of an equals f of a is a unique homomorphism that is already shown, and the image of f bar equals the image of f that is already shown. The kernel of f bar equals kernel of f mod n. Mod, where's the mod? That is already shown. What else? And we have shown that there are actually two statements that we have shown. We have shown that f is epi if and only if f bar is epi. F bar is mono if and only if n equals the kernel of f. these two combined. So baliktad na to. I don't like this. So diri ang yeah. So these two combined. So when F bar is epi and mono, what do you mean? Say that F bar is iso. Is an isomorphism if F is epi and equals the kernel. So that's anong tawag dito? The last statement you have to show. That's already shown. Okay. So let's go back to the call this diagram. So we have a for homomorphism F from G to H, a homomorphism of groups from G to H, and we have the canonical homomorphism pi from G to G mod n, and then there's also a homomorphism F bar from G mod n to H. So what does it mean? Okay, so how do we use this result to prove the fundamental first isomorphism theorem? So basically, um, about we are given a function, that function. We are given a homomorphism from G to H. We can restrict this homomorphism from G to its image. And this restriction is surjective. It's an epimorphism, right? It's an epimorphism. And then, if we take our normal subgroup to be all of the kernel of F, then what does it mean? It means that, so we have, again, we have an F, a function that is epi, right? Here. We have n equals the kernel of F. And therefore, therefore we conclude that F bar is an isomorphism. F bar is an isomorphism. What is F bar again? F bar is an isomorphism. So F bar from G mod n to H. Since F, the restricted mapping of F of G to its image to the image of F, this is surjective by definition, and we take n to be the kernel, then this is an isomorphism. An isomorphism. So therefore, oh wait, not H, not H, but the image rather, the image. So F bar from G mod n to the image of F, because these are H. By the way, this is the image of F. Although it is not shown, the image of F is a subgroup of H. This is a subgroup. Maybe it will be shown later on. This is a subgroup H. So therefore, it is an isomorphism. So G mod n, this G mod n is G of F isomorphic to the image. And this is the statement for fundamental. Fundamental. Why do you say fundamental? First isomorphism view.